so in last week's lectures, we were looking at the normal distribution, which underpins a lot of kind of things in statistics and that. And then we looked at sampling, which you're thinking about as making a measurement of something, but you're giving the kind of the uncertainty. That's this confidence interval, the range of values into which you think the population mean lives. What we're looking at now is hypothesis testing. Now, the way to think about this is you have to be careful. You want to take a conservative approach. In general, it kind of takes the approach that in general things don't really change, and you need a good bit of evidence to change your mind about something. And hypothesis testing is kind of a way of formalizing that as such. Okay, so we're looking at maybe something like something is claimed to be true, and we want to test. Maybe there's a counterclaim that isn't true. Oh, this isn't working, or maybe the process is out of control, or something like that. Here we go. So consider a manufacturing company which claims to produce metal rods that have a population mean length of 2. Now we're only going to look at means. Like it could happen that there's atrocious variance here, which means that they say the average of the rods is 2, and it is, but like there's rods that are 2 centimeters long, 2 centimeters short, all this. We're not concerned with that. We're just interested in the average. Okay, this is an assertion that's been made by the company about the population of produced goods, about all the possible goods. In this section, this will be referred to as H0, the null hypothesis. And this phrase here, status quo, it's kind of like what's believed to be true. It's kind of, what's believed to be true. So we write here that the null hypothesis is that mu, the population mean, the average length of all the rods is 2, and in front of engineers, I really should have units. So suppose after using the rods for a period of time, a construction company might say, hang on, these rods aren't made to these specifications. They might put forward an alternative hypothesis, HA. Now, the alternative hypothesis is just going to be, we're just going to have 2 types. One where it's saying this isn't true, and the other one where it's saying it's bigger than 2, and the other one is that it's less than 2. Now, realistically, the construction company is probably saying, like there's other ones you can do, and if you go into certainly level 9, but I think level 8, you'll have like null hypothesis about the standard deviation, which is about the quality. So like, okay, the average might be 2, but how spread out they are, we won't look at that. So realistically, what a construction company might be saying is that, like assuming that the deviation isn't there, that actually the average length of the rods is long, or the average length of the rods is short. But here in this example, we're just going to say maybe it's just the company making the rods just saying, I don't know, is this actually producing an average length? So they'll put forward an alternative, which in this case is just that this is not true, that the average is not 2 meters. To settle this dispute, the manufacturing, so we'll just say now it's the construction company, the manufacturing company may take a random sample of n rods. From this, now n could be whatever, 20, 30, 40, 50, 100. From this they'll find a sample mean and that should be sample standard deviation, which remember approximates the population standard deviation. The question is, does the sample, so they basically do a measurement, they do a sample, does it support this or does it support this? So this process of kind of doing this is to carry out the following steps. State the null and alternative hypothesis clearly on the assumption that H0 is true. Now this is very, very, very important. So you're assuming that H0 is true. So say for example, if the rods are normally distributed, for example, that's a bad example, the sample means you're assuming for example that you're assuming in this case that mu is equal to 2. Okay, so you're going to take a conservative approach and you're going to assume that the null hypothesis is true. Depending on level of significance, we'll talk about that later, find an acceptance interval for the sample means. So you do the measurement, and basically beforehand you kind of say, okay, there's a range of values that are consistent with this being true. Now there's a chance that we take a sample where we get very, very long rods. There's a chance we take a sample with very, very short rods, but we shouldn't throw the baby out with the bathwater. Just because the average length comes in as 2.01, that doesn't necessarily give you evidence against this. Now maybe if the rods are, the quality is very high and they're all close together, in which case the sample standard deviation is small, maybe that would be evidence, but we'll see how that falls out on the wash. But basically, we look at a range of values that are consistent with this. If the sample mean falls outside this, we reject this. So you reject the null hypothesis. You say you don't believe this is true anymore, and really you have to investigate further. Otherwise, you cannot reject this. There isn't enough evidence. So suppose, for example, we're working to 5% level of significance. Now the 5%, we'll get to a little bit later on, I think. So assuming the null hypothesis, the probability that a sample mean lies outside the acceptance interval is 0.05. The level of significance is the probability of rejecting true null hypothesis. So say, so we set this up, we get this acceptance interval, which is pretty much like a confidence interval. And we set up the values. Now there's a 5% chance, say if you set it up that way, that the null hypothesis is true, but you end up just being really unlucky and picking like 20 really above average length rods. And what will happen in that case is, even though the average of all the rods is 2, you've been unlucky enough to pick all the long ones, and you're going to get a very, very big sample mean, which is outside this acceptance interval, and you're going to reject the null hypothesis. And when that happens, that's called a type 1 error. You might have heard that happening before. Okay. So and the idea is that, like, that is a chance, but the way we're going to look at it is that if you get really, really long rods or really, really short rods, now the probability that that's going to be small, and you're going to say, well, the probability essentially of the null hypothesis being true and we get this sample is so small that we will reject the null hypothesis. Okay. Yeah. So the two types of error. So there are two types of error. The first is you reject the null hypothesis when it's true. It's like throwing the baby out with the bathwater. It shouldn't happen that much, and it's considered more serious, and we'll see why on the next page. You'll see that in a minute. And then type 2 is usually considered not as serious. Okay, and here the p-value is the probability of making a type 1 error. Probability of rejecting, so probability of a type 1 error. Now, if you want to reduce that probability, so let me say something. So as p-value, let's look at the p-value. When that goes big, then the probability of type 1 goes up. So what that means is you don't need that much evidence to reject a null hypothesis, only like a slightly large sample, and you're like, If the p-value is very, very small, there's a different issue. So this means that what will happen here is there's basically, it's going to be if the null hypothesis is true, well, that's okay, but okay, so I think what happens with the small p-value is you're far more likely to make a type 2 error. And basically what will happen with a small p-value is you could get very, very large rods because the average isn't 2, actually it's 2 meters in a centimeter, but because you're terrified of throwing this hypothesis out with a small p-value, your acceptance region is going to be very, very big. You can't reject the null hypothesis, and so you should have, but you haven't. So this is the balancing between these. Okay, I think, yeah, here we're going to see a good example. So if I want to think about this really and get on my head right, I think about a murder trial. It's a perfect example of hypothesis testing. So in a murder trial, the null hypothesis is given by the defendant is innocent. So all of the evidence is considered under the assumption that the defendant is innocent, or maybe not guilty would be a better word. The alternate hypothesis is that they're guilty. Okay, so the thing with, we write it, I think we'll look at it down here. It's kind of a funny picture to draw. Yeah, let's say this is just a schematic picture up here. So say here is the person being innocent. So this is H0. Now there's lots of things that are consistent with a person being innocent. I'm going to put a circle. This is kind of thinking of a range of possibilities. So so here we're going to look at, so this is the person, someone was murdered with a gun, and this is, there's evidence shown that the person, the defendant owned the gun. Now that is evidence, but like it is consistent with the person being innocent that they own the gun. Like there's a high chance of that happening. So there's no issue. Like if that's all they have, someone's not going to go down for murder. The next thing might be, maybe the next region would be they own the gun and they were seen at the scene of the crime or in the vicinity, you know. Now again, that's probably, it's consistent with innocence, you know. I mean, that's probably what they call circumstantial evidence. It's not really like there's no motive necessarily or anything like that. But then the next one, the next region, and this probably would be what you're thinking of as the acceptance region. Acceptance interval when we do an actual question. So these are all the different scenarios that are consistent. Like it's the probability that this evidence occurs and the person is innocent isn't crazy. It's not beyond all possibilities. But once you go beyond this, out into this region, where you get more evidence, what is the probability, for example, of the person being innocent, owning the gun, being seen at the scene of the crime, and being overheard saying that they were going to kill the person? Now, the probability of someone being innocent and, say this is where the evidence is very, very small. So what we do in that case is we reject the null hypothesis and we find the person guilty. So the way it works in the murder trial is the job of the prosecution is to come up with evidence that is inconsistent with innocence in a kind of rough sense, that the probability of them being innocent and all this evidence being there is very, very small. And that's what they kind of mean when they say beyond all reasonable doubt. Like all of these things are in reasonable doubt. The probability of someone being innocent and having all that evidence in there, like there's still some doubt, maybe they didn't do it. Okay, now what are the errors? So the errors are, a type 1 error is when you find them guilty when they're not. So that's just, now the probability that is small, that's, now obviously there isn't they don't put a number on this in court, but they want to make it as small as possible, and that's the p-value. So, what am I saying here? So, a type 1 error is basically when you convict an innocent person. It can happen. It does happen. And it's very, very regrettable. And so what you do is you do proof beyond reasonable doubt. Now, the balance then, the other side of it, is when you make the p-value very, very small, so that means going way beyond the reasonable doubt, you've got chances of type 2 errors. And a type 2 error is when you can't reject the null hypothesis, so you find them innocent when they're actually guilty. And like it's probably a good different personality types. Some people, that they won't care about so much about innocent people going to prison. They just want to definitely catch the bad guys. But when you definitely want to catch the bad guys, innocent people are going to go to prison. And if you want to avoid innocent people going to prison, you are going to have to let some people go. And there has to be a balance between them. Okay, so this is how I think about hypothesis testing. Right. So now let's actually do it in an engineering context rather than a criminal law context. So we're going to be looking at samples, because remember what we have this population mean, and we're going to look at these things. So I'm going to be recommending a t distribution, but when the sample size, so like they look at 50 rods bigger than 30, you can use a z thing. So what we're going to look at here, I don't know what this a shouldn't be here really. Yeah. Okay, so here is mu, and because, so mu is a specific number, like it was, for example, 2 meters. And this graph is the distribution, I don't know where I got this graph from. This is the distribution of sample means assuming H0, that the mean is 2. So there's a whole range of places where you expect to find sample means. So maybe if I go between here and here, something like that. Now these numbers, of course, is going to come from things that we saw previously. It's going to be a number of standard deviations. So we're talking like this one might be mu, which is the 2, plus t. Now t will be related to the size of the sample and the significance level. Numbers, and what's the standard deviation of sample means? As before, it's sigma over root n, and the sigma is approximately the sample standard deviation, and then this one is backwards. So we actually drew this picture before. Okay, so this is, let's say, for example, e.g. significance level of 5%. 95% of the sample means are in this region. There is, by the way, a slightly different way of doing hypothesis testing, but this is the way I like to do it. So 95% of the sample means are in here if you assume that the null hypothesis is true. So what we do is, if we find that the sample mean is anywhere between these two numbers, there's nothing especially unusual. But if we get something out here, or over here because I have more space to write. So this is a very, very small sample mean, a very, very large sample mean. The probability, even this tail, probability, assuming the null hypothesis, that sample mean here is 2.5%. Very, very small. And usually you might push this to 99% or even 99.8%. So that maybe this is a 1 in 1,000 chance. And this is a 1 in 1,000 chance. So what you kind of say is you say rare events don't happen. Now 2.5% isn't that rare, but you can push it, as I said, to 1 in 1,000. Rare events don't happen. So if I find the sample mean out here or out here, I say, I say it's not that something rare has happened. It's that this is not the correct position of this is not the distribution. The null hypothesis is true. So if you get this, so if you get a sample mean in there, you will reject the null hypothesis. Now, essentially what you're saying is that this isn't what the graph looks like. Maybe the graph actually looks just something else. Maybe it actually looks like this. Now, the alternative hypothesis doesn't specify what the population mean is. It's just saying it's different. Okay. So this is how it works. Let's do some questions. So test at the 5% level of significance. So that's p is equal to 0.05, 5%. The claim of local politician Harry Riley J that the average resurfacing period in, now this was the question we saw in a previous, in a particular county is the same as the national average, given that a sample of size 50 yielded a sample mean of 6.75 and a sample standard deviation of 1.8. So basically the situation is someone's giving out that our roads are not being resurfaced. We know that the national average is 6 years, so we're saying that it's not 6 years. So Now here probably we should say that it's longer than 6, but we'll do that a bit later. No, we're just saying it's not 6. So we should state the null hypothesis, what's believed to be true, and certainly the what's believed to be true somehow is that the average is no different than the national average. The alternative is that it's not true, and then we'll set up the acceptance region, which is essentially this formula here. Okay, so the null and alternative hypothesis is that the average resurfacing period is 6 years, and the alternative is that it's not. Maybe later on we'll look at maybe it's greater. So I set up the 95% acceptance interval for the sample means. So all of our sample means are 95% of them. Where are we getting 95%? From the 5%. Mu minus t sigma over root n, mu plus t sigma over root n. We want a 95% interval. I need to get our t table. So we want 5% in the tails, and we're doing 2 tails here because we're just saying it's not equal. So it's 5% in the 2 tails. The sample size was, they looked at 50, so we should go to 49, but which we can't do that. So we go to 50, we get 2.009. Mu is 6, sigma is approximately s, the sample standard deviation is 1.8, and n is 50. So let's calculate these numbers. So we get, now we take mu to be 6 because we assume the null hypothesis is true. 6 minus 2.009 sigma, which is approximately s, is 1.8 divided by root 50. And maybe I'll use this interval notation here. And then 6 plus 2.009 times 1.8 over root 50. And this is the acceptance region, or acceptance interval. So this is a range of values that is consistent with the county having the same average. Now, like, you get the sample where, well, we'll go back to the sample in a second. So 6 minus 2.009 by 1.8 divided by root 50. I'll just do 4 significant figures, 4.89. What the hell happened there? 5.4, sorry. 5.489. And then, I don't know what happened there, sorry. And then the plus one is 6.511. So like getting 6.5 years is bigger than 6, but it's not inconsistent. Getting 5.5, well, that's probably not what they're thinking about, but getting 5.5, it's not especially unusual if the average is 6. These are all kind of consistent with the average being 6. 95% of the sample means will be between these two. But what's happened here is they've gotten 6.75, which is way up here. And the probability that the average in resurfacing period in the county is 6 years, and the sample gives you 6.7 years, is very, very small. Well, we're saying 5%, less than 5%. It's actually less than 2.5% up here. And we say, look, that's not what's going on here at all. So we reject the null hypothesis because 6.75, this is the sample mean, lies outside this acceptance interval, so we reject the null hypothesis. Now what happens now is really we have to go and make more measurements, but we just stop here in terms of the hypothesis testing. Okay, got a lovely example here which we'll go into the next lecture.